When you're using Google Maps to find a way to your friend house, you are searching through a geodatabase. When you are on the YouTube and trying to type some keywords for the video that you're looking for, you are technically searching through billion of records of data. When you are in a game trying to figure out where is a treasure, you are searching. When you are using, for example, Spotify or Google search engines or all these kind of things, you are all the time searching. When you wake up every day, you are searching for a better life. Entire of human life is based on searching. And the question is, when we want to go to the digital world, how we can teach computer to do the searching in the best and efficient way. And that's what I'm going to talk about it. Well, remember we talked about computational thinking in the first chapters, and then we went through four cornerstones of computational thinking. The first one was decomposition, and then pattern recognitions and abstraction, and designing algorithm. So it's a very important skill to know how to design an algorithm for problems such as searching, right? And in this second chapter, I'm going to go through some popular algorithms like searching, sorting, and some other stuff. But today is about searching. And I picked up two famous search algorithms, linear search and binary search. Before that, let's talk a little bit about why not when we want to search about something, we just look at all the data that we have one by one to figure out which one is our favorite data, the one that you're looking for. But think a little bit about it. If you are an organized person, you never do such a kind of things. Let's say you have a kitchen, a big kitchen, huh? And a lot of cabinets, and you're looking for salt. What are you going to do? If you are messed up and not organized, you're going to go through all the cabinet, and you have to search one by one. And you're going to do this every time? This is not going to work. This is not a solution. People, they bring a little bit of structures. For example, we know that this cabinet is for oil. You're never ever going to find salt in it unless you messed up. And this cabinet is for spices. So by bringing a little bit of structures, you try to save your time, to not go through entire of the kitchen for that salt. A structure is good. Organization and bringing forms into your data is really good. Computers, they keep doing searching. They do this searching all the time among many data. For example, when you are in a kind of online shopping a website or e-shopping and you're searching for products, you may type the name of the products. You may search based on the color. You may search based on the size or brand or the category. So the algorithm behind that website should keep searching over the database, cross the database, to bring those best matches based on the query that you gave to the computers and based on the keywords that you gave to the application. So this is not a good way you go through entire data. And data is not just a little bit or few bit. You know what? We have billion of websites in this planet, and how Google searching them. So definitely it's not a kind of one by one because you're going to take your time and you're never going to finish this. So we need some solutions. We need some heuristics to apply to this searching. So the data size is really big, okay? Nobody go through all of it. Now let me talk about two common algorithms. The first one that I'm going to go through it called linear search algorithm. Okay, it's very simple, and maybe it's the dumb one. It's just linear, means like you go through whatever you have and then search and then pick up the one that you're looking for. Looks like you go to your kitchen, you don't care this is a spices cabinet or this is oil, and imagine you're looking for salt and you need really salt for your food. And then you start from the first cabinet, he's not here. You go for the second one, he's not here. Third one, fourth one, fifth one. You see where I'm going with this? If you are lucky, the first cabinet you open, that is your salt. You're going to get it. But what if the salt is not in the kitchen at all? Then you have to search entire of the kitchen and get really angry and tired and hungry. And then, oops, I left it in the dining room. You see what's wrong with the linear search? Worst case means when the data that you're looking for is not in the database, then you're going to waste a lot of time because you have to go through entire of list. There's no any other information that you want to utilize it to find the data. And if you're lucky, you're going to find it in the first match. So I do have a kind of animation that presents how the linear search works. So let's go through that one. Look at here that let's look at this animation. Maybe it's good to see the whole thing one time. Okay, imagine you have a bunch of numbers. Okay, each number can present a product, a person, a movie, a video, whatever you like, okay? And then we're looking for 33. So we know that there is a 33 here, but what we're going to do, linear search. We start from the first element. Compare 33 with number 10 to make sure that if they are same or not. We see they're not the same. So then is not the same, then we go for the next element. If 33 is equal by the second element, no, it's not like that. So we go for the third. Is it the same? No. And then we go for 26, 27, and 31. And finally, yay, we're going to get it on 33. So look at the animation. So here we find a match. Here there is a match between 33 and this element. So look at this. How many steps? 1, 2, 3, 4, 5, 6, and 7. So this should happen. This is a requirement for us to reach to 33. So let's look at the animation one more time. And then finally this. So this is how linear search works. It's very simple. Look at the first element and the next element and continue till we find our guy. Or we reach to the end of the list, the worst case, and say, oh, sorry, there's not found. So now, if you remember, in computational thinking, we talk about flowchart, and I draw a flowchart and explain. I'm going to show you guys flowchart for binary search. So let's just look at the flowchart for linear search. So I just explain quickly here. Remember, this is the beginning of the algorithm. So, and imagine we have this list, and we're looking for 37. So 37 is here, right? So begin. Remember, the diamond is decision making. More items in the list. I'm asking, is there more items? Yes, there are a lot of items. So we come here, check next item. So next item is 20, the first one. Found what we want. No, 20 is not 37. So no, we're just going to back. We're going to come again here. So more items in a list? Yes, there are more items. We just passed 20. Now we're in 35. So check next item. So now we're 35. Found what we want? 35. No, sorry, it's not a 37. So no, we go. And then we check that if there is more items in the list, yes. We get the next item, which is here, next item. We see the counting, next item. Found what we want? Yes, 37 is exactly what we were looking for. So yes, return item and end. So that's how the searching will be terminated, will be finished because we found the items. But what if the item is not in the list, huh? Take a look again. So if we're looking for something else like 73, which is not this, so we're going to go for the next. So we're going to go for the next. We're going to go for the next. We keep looping here. We go for 40, 45, 50, 51, 55, and finally 67. And then, no, we're back again here. More items in the list. No, it's not. So we're going to come here and not found and end. So this is linear search. I think it's very intuitive. You intuitively can get it. We just go to, imagine a bunch of cards, you check them one by one. That's all. But now we're going to be a little bit smarter. We're going to be a little bit faster. And we're going to try to change things. The next search algorithms I'm going to talk about it is binary search. Let's talk about a binary search and see how binary search works. Before that, let me tell you something. Binary search has a kind of requirement. What if the data that you have, lists of numbers, for example, lists of codes, it's already sorted from the smallest to the biggest one? Imagine, what if we have such a kind of information about our data? For example, if you're looking into your contact list, imagine all of your friend names sorted alphabetically. That means A, and then B, and then C, and then D. You know such a things. When you have this piece of information, so if someone asks you to search for Tom, Tom is T. You're not going to start from the A because you know that why should it waste the time in the A section? Or B, you're going to jump and go to the T section. And then you're going to save the time, right? This little information make the whole things faster. So binary search is designed based on this principle that what if the data that we collected already in our database is sorted? And we do this all the time. So let's see how a binary search works. I have another animation to show you to you guys. So look at this animation. Let's say we're looking for 47. You see the data is sorted 0 to 53. 4 is greater than 0, 7 greater than 4, 10 than 7, and so forth and so on. So 53 is greater than all of them. So what we do is this. It's very smart, guys. It's really, really interesting the way that this search algorithm works. We pick up the midpoint. The midpoint is very important, which you can see here. And then we compare it with the 47. Why we pick up the midpoint? Because midpoint is the best place that I can create 2 half. two halves. One is in the left side and one is the right side. And then when I compare 47 with 14, I have to ask this question: if 47 is greater than 14 or not? If yes, so definitely it's not here. Why should I look at the first half? Why should I look at the left half? I don't want to waste my time. I know 47 is greater than this, so it should be somewhere here if it's in the list. So that's the beauty of when you know your data is sorted. And if the answer to this is yes, is lesser than 14, so then you're going to come for this part. For example, if rather than 47, we were looking for 5, 5 is lesser than 14, so we have to search here. So because 47 is greater than the 14, so we skip this first half, and now we go for second half. You see that suddenly 50% of your data, you can just forget about it. And that's a great thing, because it doesn't matter how big is the data, suddenly you just say goodbye to half of it. And now look at the second half. So why not apply the same strategy for the second half? What do we do in the second half? We look at the middle guy. Well, here is a little bit tricky. You see, because we have even number of elements, 1, 2, 3, 4, and middle guy, you don't know, you go for 45 or 47. Okay, we can do this. Whenever the length of our list is even, and then we do have such a kind of situation like that, that means either one of this can be middle guy, we go for the first one, okay? It's just something we try to be persistent whenever we face with such a situation like that. It's okay, you can go always for this one, but I want to go for this one. So this is the middle guy, and I compare 47 with 45. 47 is greater than 45, so this part, I can ignore it, and I can go for this half. So again, 50% of the 50% I can ignore, then I go for this part. So now 25% of data available for me. So just going to do that, and I will run it. And I will go for the last half. I have two elements. So again, remember, each one of them can be the middle. I go for the first one. And then, yay, we found it. And that's really great. But look at how interestingly we reach to this point. Let's look at the animation again. So middle point, 47 greater, and then 45, and then this, and then 47. I want to count how many steps we went through to reach to 47. It's very important. You can count it, how many steps or how many checking with it, how many times we check or we try to do matching. Okay, so let's look at the animation. One time here, you check one time here. Second time, and third times. Only 3 steps. By 3 steps, you found the data. What if you wanted to do linear, huh? If you wanted to do the linear, you have to check with this 1, 2, 3, 4, 5, 6, 7, 8. You should do 8 pattern matching, 8 times checking to reach to your data. But now when you use the binary search, you did it immediately, super fast. So you can feel that the algorithm is much, much faster. And if you want to see a flowchart for this, let's look at the flowchart. Okay, you can see the flowchart is a little bit more than the linear search, of course. So begin, again, more items in a list, yes. Find the midpoint. Remember we picked up the midpoint and found what we want? No. And then we check, is it before midpoint? So if it's before or lesser than the midpoint, so yes, discard second half. Discard second half. Second half is the other half because it's lesser than the midpoint. So we're just going to look at this part. We don't need to go to this part. So that's what that part of algorithm does here. So, but if it's not before the midpoint, we discard the first half and we focus only on the second half. Again, we ask same questions, more items, find the midpoint of the new half, and then is it what we wanted? No, and again, divided by 2. So you can see that every time we divide the list by 2, and we get the new sublist, and again, divide by 2, and then finally we reach, huh? So you may find the elements, or you may really reach to the very ends, and you can't divide it by 2 because you have just one element, and that one element is not what you're looking, so you say not found. So this is binary search. Linear search and binary search. Now it's time for comparison. I want to compare these two algorithms just quickly. Let's say we do have 1024 elements in our list. Okay, 1024 elements. By the way, 1024 is 2 to the power of 10. I have a reason I choose this number. Okay, so 1024. And then you want to go and search for an element using linear search, right? And imagine You are not lucky. Okay. And the elements you're searching is not in the list. So what are you going to do? You're going to go through all these 1024 to the very end, and then, okay, it's not there. Or you are lucky, maybe the first search that you do, the first element is what you wanted. So something between the first and 1024. So there's a way that we can calculate the average. Okay. But anyway, I don't want to talk about that now. But now let's say we want to apply binary search. Binary search has that requirement of your data must be sorted. And then if I'm going to do that, so I have it divided. This is the list, 1024 divided. Maybe then I have two sublists. Then I check it's lesser, I will come here. It's bigger, I will come here. So then again divided by 2. Then again divided by 2, divided. So the question is how many times I can divide this 1024 by 2 till I reach to one element or nothing. 1024 divided by 2, 512. Divide by 2, 256. Divide by 2, 128. Divide by 2, 64. Divide by 2, 32. Divide by 2, 16. Divide by 2, 8. Divide by 2, 4. Divide by 2, 2. Divide by 2, 1. And then finish. So how many times I'm going to do that? It's 10 times. Because you can use logarithm. Logarithm of 2 power of 10 is 10. So it means maximum by 10 steps. You can find the data all the time. You can say exists, or you can say does not exist. Found or not found. Not more than 10. So from 1 to 10, that's your best chance. So it's really, really interesting. This is the power coming from binary search. But of course, has this requirement, the data must be sorted. You may say that, okay, sorting data by itself has some kind of overhead. You're right, but there are some interesting and neat techniques that when we collect data, we put them in the database in a way that they are sorted. So that means we do it one time, and then all the time when we want to search, we're so happy and fast and smart, and that's the result. So that's not that much big issue, right? So this was about searching algorithms. I talk about 2 searching algorithms. There are many more searching algorithms. Just I just picked up 2 of them because these 2 are just maybe easy to talk about them. So you have to just get this sense of how we devise an algorithm, how we solve the problem. One in a very naive way, like linear way, one a little bit smarter, like a kind of binary search. But that's very important because every day, everything you do in your computer is engaged with searching, in the applications and everywhere. So if we can do it faster and better, of course, why not? So this was about searching. Please think about it and ask me any questions about it. I may try to create some contents based on your questions, and I will post some quizzes and content about this searching algorithm. Take care, you beautiful people.